Hi everybody, I'm Johnny Giraldo. I am PhD student at the University of La Rochelle, and my PhD advisor is Professor Thierry Bumas. Today I'm going to talk about our paper on the minimization of Sobolev norms of time-varying graph signals, estimation of new coronavirus disease 2019 cases, COVID-19. Then basically the outline of the presentation, we are going to talk about the motivation and the problem, some basic definitions in graph signal processing, the algorithm, the overview, time-varying graph signals, and the Sobolev norm of time-varying graph signals. Finally, we are going to talk about the experimental framework and the results. Then, what is the motivation? The idea is trying to incorporate a graphical information in the estimation of new COVID-19 cases. The models associated with the mathematical of infectious disease usually have exponential prior assumptions in the number of new cases. Our idea is trying to incorporate graphs in the estimation of new cases. And our prior assumption is that the number of new cases is smooth in the graph, in our case, in the spatial domain, and is also smooth in the time. Then basically, the problem is that we are going to try to estimate the number of new COVID-19 cases in some cities represented by nodes in the graph using spatiotemporal information. Then some basic definitions of graph. A graph can be represented with a set of nodes and a set of edges. We have some important matrices like the adjacency matrix, the degree matrix, and the Laplacian matrix. For example, the adjacency matrix is going to tell us the structure of the graph. Then, for example, if we have an edge from the node I to the node J, we are going to have a weight Wij in that matrix. The degree matrix is a diagonal matrix in which each element of the diagonal is going to be the sum of all the weights arriving to that specific node. And the Laplacian matrix is the degree matrix minus the adjacency matrix. Finally, we also have the graph signal, and a graph signal is a function that goes from the set of nodes to the real value, and we can represent a graph signal with a vector in Rn. We are going to work with sampling and reconstruction of graph signals. For example, in the sampling step, we want to choose some nodes of the graph. And in the interpolation or reconstruction is the same. In the reconstruction, we want to interpolate, to reconstruct, to recover the original graph signal as better as possible with the samples that we have from the sampling step. Then that's basically the problem of sampling and interpolation of graph signals. Now, the overview of our algorithm. We have a graph, and for each node in the graph, we have a time series. Then, for example, we have the US and we have a time series giving us the number of new COVID-19 cases. We have the time series for France, a a time series for Italy, a time series for China, and so on. Then basically, we are gonna reconstruct all the time series using the graph, the spatial information, and the temporal information. And we are gonna do so using the minimization of the Sobolev norm of time-varying graph signals. Then basically, we have this X matrix that is the time-varying graph signal, in which we have X1 is the graph signal in the first day. We have X2, that is the graph signal in the second day, and so on. We also have another important function, the smoothness function of X is the trace of X transpose Laplacian times X. This comes from the sum of all the Laplacian quadratic form for each graph signal. The smoothness of a time-varying graph signal is the sum of the Laplacian quadratic form of x1 plus the Laplacian quadratic form for x2, and so on. Q in 2017 introduced the temporal difference operator, that is this matrix in equation 1. They introduced this temporal difference operator trying to get the information in time. And for example, here we have x times d, that is x2 minus x1. It means the graph signals in the second day minus the graph signal in the first day. X3 minus x2, and so on. And finally, we have a J matrix, that is the sampling matrix for the whole time-varying graph signal. And now, our algorithm is the minimization of the Sobolev norm of time-varying graph signals. We extended the definition of Sobolev norm for the time-varying graph signals as this equation 3. Basically, we have the trace of this function, and this comes from the sum of all the Sobolev norm for each graph signal. And basically, the Sobolev reconstruction for a problem for time-varying graph signals is formulated in equation 4. And basically, we have the minimization of this first term is for the trying to reconstruct the graph signal as similar as possible with the samples that we have, where this circle J circle X prime, this X hat, sorry, this circle is the Hamadar product between matrices. And we have this second term, that is the Sobolev norm. And notice that here we are using the temporal difference operator. And in this case, we are trying to incorporate a spatial and temporal information. Then with this, we are assuming that the time-varying graph signal is smooth in time and in the spatial domain. The nice thing about the Sobolev norm is that this problem has a better convergence rate than using the Laplacian alone. That is because the condition number of the Sobolev norm is better than using the Laplacian. That is because the first eigenvalue of the Laplacian is 0 when we have connected graphs. Then the Laplacian is ill-conditioned, but when we add this epsilon times the identity matrix, we are improving the condition number, and this give us a better convergence rate in the optimization problem. We have the proof of this fact in the paper. Finally, the experimental framework, we test our algorithm in the global and in the US COVID-19 databases provided by the Johns Hopkins University, and we also test our algorithm in a database of sea surface temperature and daily mean concentration of particulate matter, PM 2.5 in California. We compare our Sobolev algorithm against Q method and natural neighbor interpolation. For each database, we make one experiment to check the performance and one additional experiment to check the convergence rate between the Sobolev norm and the Q method. Then here we have the results. In the first row, we have the mean square error for COVID-19, for sea temperature, and PM 2.5 concentration. We can see that our algorithm is better in the case of COVID-19. And the second row shows us the average number of iterations required to get convergence. In that experiment, we can see that our Sobolev reconstruction algorithm is faster than Q method. And in PM 2.5 concentration is slightly better than Q method. In summary, this work introduces concept of graph signal processing in the estimation of new COVID-19 cases. Our algorithm solves the minimization of Sobolev norm of time-varying graph signals. And our algorithm is shown to have a faster convergence than other state-of-the-art algorithm, as we show in the results. Finally, for future work, we want to introduce concepts of product graphs, trying to explore and study the problem of sampling in time-varying graphs. That's it. Thank you for your attention. Let me know if you have any question.